cloud.
In regard, I'm doing it now. So.
All right, great. Well, welcome everybody. Thank you for being here for our webinar. I'm joined today by Krishna Kumar, who will co-deliver this webinar with me, and we're excited to bring this to you. This format is a little different. If you've attended some of our other webinars, we've used a Zoom webinar format. This one is just a Zoom meeting, so you can all, turn on your camera and unmute if you have questions. But please, during the webinar, just keep muted so that it's not disruptive to everybody if there's background noise or anything like that. One thing is that you should have received an email, let's see, just yesterday from Tim Cockerill with some instructions to connect to a Jupyter server for the webinar. It turns out that if a large number of people try to connect to Jupyter and DesignSafe all at the same time, it can create some problems. So what I'll do now, if you haven't already connected to a session, you should go and do that if your last name starts with A through L. I think half of us can do it at a time. So go ahead and do that. And then maybe after I finish the introductions, I'll have M through Z go ahead and do the same. If you are using your own local Jupyter hub, you can do that too for parts of it. But there is part of it later on in the webinar that will use data that's published in DesignSafe. And if you're using a local instance, your code won't work for that. You'll have to be on the DesignSafe Jupyter hub. All right, so I'll go ahead and share my screen and show a few slides here before we get going. So this is a DesignSafe webinar. This is our second one of this semester. So thanks everyone for coming. We do appreciate your feedback. So here's a QR code. If you take a minute to scan that, there will be a survey at the end. I'll show this QR code again, and we'll paste a link also in the chat. I know a lot of you would probably prefer not to complete the survey on your phone, but on your computer instead. And it's hard to scan a QR code with your computer. So the webinar is delivered by Krishna and me. You all have seen our bios here briefly. We've both been very involved with DesignSafe, and so it's a lot of fun to be here together with Krishna. So the reason we're doing this webinar is that Python is very popular. A lot of people are using it, and there's a lot of powerful packages. It's the primary language for machine learning and AI. But there are some limitations of Python. It's a great tool. We're not here to tell you not to use Python, right? But there are some limitations because it's an interpreted language rather than a compiled language. And so it has some things that are not very efficient and can be pretty slow. I first discovered this when I translated a code that I had previously written in a compiled language into Python, and it was way slower, right? Instead of running in, say, less than a second, it was taking 45 seconds to run, which is kind of a big deal, right? If you can do it in less than a second, that's much better. So what we're going to do is explain some of the reasons why Python can be inefficient and some really basic ways that you can make it more efficient using vectorization or just-in-time compilation, or JAX and Numpy and so forth. And we'll also show a little bit of code that could be used on some of our more high-performance computing resources. We do have now HPC Jupyter instances for both CPU and GPU nodes that run on our Frontera machine at TAC. And then I'll do a demonstration at the end that show you directly how to access DesignSafe published data, right? So one way of getting data, we have over a petabyte of data now in Corral associated with the DesignSafe project. One way to get it is to download it, right? But you can access it directly. There's no reason to actually download published data. You just need to know the path of where to find it, and then you can pull it into your notebook. Since the data is published and has a DOI, that path will persist. So I'll show you how to get to different places to access data sets. And I think that that's it for this one. And I will switch now. All right, so if you haven't yet spun up your Jupyter Hub on DesignSafe and your last name is M through Z, please go ahead and do that. Hopefully we won't crash the system. I know Krishna had a webinar that kind of crashed the system in the fall, so we're trying to avoid that that same fate this time. All right, so I will share again and move to, let me, before I share, I'm just going to paste the link real quick to our GitHub Jupyter book. Um,
Yeah, I pasted it. It's come.
did you get it?
Yeah,
Okay.
I put it here.
Okay, perfect. Thank you. All right, so we have set up this Jupyter book in GitHub. Krishna and I have collaborated on this together, and this is where you can find all of our background information, including links to our notebooks. So I'm going to click on this link right here that opens up our Jupyter book. Jupyter books are really cool. It's a way of putting together notebooks into a single sort of publication. So here's the background of our webinar today. And I'll move on to this next section and then hand off to Krishna for the vectorization part. And Krishna, feel free to weigh in. I may say things that aren't quite right. I know you've been changing this today, so some of this is a surprise for me too, a little improvisation. So the first part is about compiled languages and interpreted languages, and then just-in-time compilation, or JIT. And so this is really critical to understand why Python can be very slow if used in a certain way. So first, we'll start with compiled languages. This may be like what you learned when you took computer science or your basic programming class as an undergraduate. These are languages like C, C++, and Fortran. And what happens with a compiled code is that you write the entire source code, and then you tell the computer to compile the code into machine code or binary executable that can then be run by other users, and you can share that executable with other people. So at the compile time, the compiler analyzes the entire source code, right? Every line of code is analyzed, and then it knows what to do to make this binary executable for you. And that depends on your computing architecture, right? What kind of operating system are you using? What's your hardware? And so forth. And then when a user runs that executable file on a suitable machine, it runs and produces some output like hello world. That's always the first computer program that we run, right? So C, C++, Fortran, those are compiled languages. They're very performative, right? Because the compiler has figured out how to make the binary executable very efficient ahead of time. And so when you run these, they're very fast. And if you have an application where execution speed is critical, it should be done in one of these languages. You know, like for example, our OpenC's program that runs on DesignSafe is all written in C++, right? It is not written in Python or some other kind of interpreted language. All right, let's go to interpreted languages. So an interpreted language operates a little differently. You write the source code maybe in a similar way, but with some exceptions. There are differences that make source code easier to write in interpreted languages. Then you push the run button. So you write your Python code here, you push run. So instead of compiling all of that source code and then running it, the Python uses an interpreter. So at runtime, as it's running through every line of your code, the interpreter is doing some work to figure out what it is that you intend to do with that line of code, and then it executes that line of code and you get results out. So for example, in Python, you don't have to declare the type of your variable. You don't have to allocate memory for arrays, right? All of those conveniences that come along with developing code in Python are because the interpreter is doing extra work when you push the run button to figure out what it is that you want to do. So interpreted languages make the code development part a bit easier, but they make the performance of the resulting code slower, right? So there are some trade-offs there. There is hybrid, right? This is a hybrid between interpreted and compiled languages. And so you can develop your source code and push run. And what it will do, the interpreter will run, but then it will also do a just-in-time compile operation. So it takes a little bit longer the first time you run this, because in addition to interpreting every line, it's compiling parts of the code into machine code ahead of time and then executes. The benefit of JIT is that now the next time you come back and run this code again, it's already pre-compiled a lot of it. And so it will run much more efficiently and faster. So JIT is nice because it requires very little modification to your source code. You have to put like a little flag at the top of your code sometimes, and that's all it takes. And then you get much more performative code in the end. So here we have some pros and cons, just so that it's clear, what we're talking about and why we're having this webinar today. So compiled languages are faster because the source code is translated ahead of time and you don't have to worry about all this runtime processing that happens. The problem is that it's a little hard to write the code, right? If I could write code without having to declare variable types, allocate memory, do all that stuff, wow, that would be nice, right? So the interpreted languages provides that support at the expense of some performance. And then JIT is kind of a hybrid. So we have this pros and cons table here. Compiled code is better for execution speed, not as good for code development because you have to write extra lines of code and do all those sort of annoying bookkeeping tasks. A benefit of compiled code is that you can keep your source code private, right? If the only thing you share is the binary executable file, nobody sees your source code. So when you go to download programs, like for Windows or a Mac machine, you just download the executable. You don't get the source code with it. So nobody could steal your source code. As a result, though, it's not very portable, right? The source code is not there. If the executable was not configured for the machine you're working on, you won't be able to run it. Interpreted languages are not as good for execution speed, better for code development. You can't keep your code private, right? The interpreter interprets the source code at every step of the calculation. So you have to share your source code for an interpreted language if you want to share it with people. It is more portable, right? So if you take a Python script, it will run on Windows, it will run on Mac, it'll run on Unix. As long as those programs have Python installed, it'll know what to do. All right, just in time has some benefits of both. So execution speed, JIT is faster partially, right? It'll actually be maybe a little bit slower the first time you run it, but then in subsequent runs, it'll use all of that compiled machine code and run faster. So overall, it's a check mark. For code development, JIT is just like the interpreted languages, no variables to declare or anything like that. The private code, you could partially keep your code private. If you could go and find the binary executables that are built at runtime using JIT, you could just share those. But maybe it's better just to share the full source code anyway with the little flag on top to tell it to do the compilation. So it could be either way. And then portability also partially, it's more portable. That depends on whether you choose portability and private code kind of go together, right? If you share the source code, it's very portable, but not private, and so forth. So we'll move on now to vectorization, and I'll hand off to Krishna for that part and stop my share.
Okay. Let's see. Okay, so we'll talk about vectorization. I think this is where we're going to do hands-on. So let's see if we break stuff on DesignSafe. So I would like you to go ahead and click on Open in DesignSafe. So I've already pasted the link for the note for this Jupyter book. You should have it. We're going to try to write a traditional Python code and see how we can accelerate it. It's not a very complex code, and I'll do a more complex example later on. So once you're here, I would like you to go ahead, click in Open in DesignSafe. All right, great. Is that our first hurdle? Digi, this. Okay. All right. So hold on. Let me figure this out. Let's see if I can get this one to work. Okay, that works. So let me fix it in a
Keep
moment.
changing those links. It's hard to maintain the links from webinar to webinar.
Yeah. Give me one moment. I'll paste you the link you need to be on. Okay. Accelerating, and mine is called Data Depot Vectorization Exercise. Okay. Okay, this should redirect. Okay, so I'm pasting the link here. Let me know if you can click on that link and if that works or not.
I think it's working for
Okay.
me. I'm getting the spinning blue wheel.
All right, great.
Yeah. It worked. It just opened.
Okay, perfect. I am going to do a live edit of this. Okay, so if you refresh your notebooks in about 2 minutes, we should have an updated version. Okay, live fixing Jupyter notebooks. Okay,
Did you update
so
you updated the GitHub already?
yeah.
Yeah, Carl says which to select, updated or classic. I think updated is probably better, but I think that this will work in classic. So if you're in
it will
classic,
work in classic too. Yes. So yeah, please feel free to paste any comments. Professor Brandenburg will look at it, and then like if I miss it and don't see it. Okay. All right, so let's go ahead, assuming everyone's logged in. We'll talk about writing a very simple function. We're going to calculate the sine value of 2 pi frequency times the time. So that's the signal we're going to generate, sine 2 pi ft. So we're going to define the time based on a dt, which is a time step in seconds. So we are using like 5e minus 3 here. And then we are multiplying it by about 10 million steps. So we're going to do the same calculation of 2 times pi times the frequency is 2 hertz, and we're going to change the time interval at each time. So we're going to run this. So you're going to import Numpy and time. The good thing about a Jupyter notebook on DesignSafe is some of these packages are already installed for you. So you can just do import NumPy, and NumPy is already installed. If you do find something which is not already on DesignSafe, you can always do a pip install user, so it installs locally to your user account, and then name of the library something like Jax. But for now, we have NumPy installed, but like here's your reference command in case you want to install any of the typical libraries. Okay, so for 10 million steps, the first thing we're going to create is a there should be servers available, so maybe click refresh if they're not opening. So is there a like poll option? No. How many of you are still waiting for a server to start up? Okay. everyone else. If you're facing trouble, please message us, and if you can, please send us your DesignSafe ID, and we will see if you are stuck. Or Scott, do you want to ping Tim if they send you the ID? Is that okay?
Yeah, I can do that.
Okay, thank you. And you can always, like, while it is spinning up, you can always look at the completed version of the code in our Jupyter books. So that's the reason why we provide you with these completed versions of the code, so you can always follow along and see what's happening. So it's just a live execution that you're going to see, so you're not missing out so much in terms of what command to write. So you always have those there. So let's go ahead, run this. And what the linspace, if you haven't used the linspace command before, does is basically it evenly distributes or divides your domain space. In this case, we are dividing the domain of size 0 to time t, where time t is defined by dt, which is 0.005 times the number of steps, into 10 million chunks. So that's how we have divided the time space. So if you go ahead and look at the time space, you can see that it's a huge array. You can check the size of your array by doing the len command, and that says it's 10 million chunks. So we already have these 10 million chunks, and you can see that it's divided in 5e minus 3. So that's exactly our dt. So at each time, we are going to compute the signal, and we are going to calculate it just using Numpy. And here we go. So the first step we are going to do, this is usually to speed things fast, even in a traditional for loop operation. So at each time t equals 0 all the way up to t equals 5,000 in increments of 5e minus 3, what we're going to do is calculate the signal value, which is 2 pi times the frequency times the time. For that, we are going to store the output in the variable called signal. We create a variable called signal2 here, and we initialize it into an empty array. So this is a recommended step. You can, of course, like append to an array. It's easier to append to an array if you have like 5 or 10 elements, but if you have like 10 million elements, appending to an array means your compiler or interpreter is going to look for spaces in memory where it has that chunk for 10 million. So initially, it might allocate an array of size 10, which is relatively close to where your operations are being done, and then realize your array size is growing. So go ahead and pre-allocate an array and say it's an empty array of size 10 million. And these two are just to keep track of time, so you don't have to do anything. So the first thing we're going to do is write a for loop. And for loop in Pythons are really simple. So you just need a counter. We're going to use the traditional variable I for a counter, and then say NP. And we usually abbreviate NumPy as NP, and we've declared that at the top, that import NumPy as NP. And we go np.arange of n. So this basically allows us to, so range command iterates and creates a list going from 0 with increments of 1. And traditionally, you would write it like 0, n, 1. But the default starting value is always 0. The default increment is always 1. So you can also write np.arange n. So this is equivalent to saying np.arange n as well. Okay. So in each of the for loop, we are going to store the value of the signal in the variable signal2 at index I, and we're going to calculate this formula here, which is 2 pi times ft. Right. So np.sign calculates the sign function. So it's 2 times the frequency, 2 times the pi, and then the frequency f, which is defined to be 2.0. And each time we're going to take the array t and each individual element in that array. So make sure to close the parentheses. So once you have this code, go ahead and run it. This is going to take a while because we are running it 10 million steps, and each time it is going to take the value of individual elements in the array. In this case, the individual elements is an array T, multiply it by 2 times pi times f, and store it in a new array, which is signal2, which has been initialized with 10 million elements. So it nearly took like half a minute, 27 seconds to run it. It was a very simple operation. All we did was write a for loop that ran 10 million times, but computes 2 times pi ft. Okay, all right. So why was it slow? Other than we did write it in Python, like Professor Brandenburg said, it's an interpreted language, which means every time it is going to and running the code, reading the code, it's going to convert it into an interpreted executable engine. And the interpreter has its own execution engine and runs this command over and over again. And because it doesn't know we have a big supercomputer that runs it, there is a, we are still using a single node on a supercomputer. And at this point, like the Jupyter notebook you're in, that machine is shared by others. Don't worry, your data is not shared, it's the compute that is being shared. So we do have like a big machine that can distribute it. So why don't we try to make use of it? And this is running in serial, although the computer has multiple processors. We are using one single processor and one single register that does the computation. So the next step, what we are going to do is basically use something called vectorization. And since like early 2000s, we've have machines that are capable of doing vectorized operations. So that's what we're going to see. The first step is to vectorize our code and make things run faster. Okay, it might be easier to show it here instead of like a huge window. So I'm going to use this screen here. All right, let's see, is that big enough? Okay. So what is vectorization? Vectorization is a technique which is used in numerical methods where you can, performing the same operation like using an array, either manipulating an array or something else, where doing an operation like n number of times. So it's basically called single instruction multiple data, or SIMD. Single instruction because in your for loop, you only have like one set of instruction. You can have multiple things in your for loop, but what we're basically saying is the operation is still exactly the same. It's only the data that changes. And especially data listed in an array, so it's contiguous. An array is always contiguous in a computer memory, meaning it is located continuously in the computer memory, so the computer can go element 0, element 1, element 2, element 3, and so on, without having to look at different locations in memory to do the operations. So the way we leverage it, vectorization, or the way we make things faster using vectorization, is using the registers in the computer to do more than one operation at a time. Typically, nowadays, most computers, so this is since 2010 or 2008, so almost for a decade or two, decade and a half, we have computers that can do more than one operation at a time. We're not talking about number of threads, which are multiple processors. I'm talking about in a single processor, each processor can do more than one operation at a time using these registers. All right, here's what a typical register operation is laid out. Even if you're using, let's say, 32-bit operation, so floating points, which has about 10 to 12 decimal places accuracy. Those are 32-bit integers or floating point numbers. We are going to do operations on those. So a computer which has 4 registers will be laid out like this. So you can see that this computer has 4 registers. And each time as we go through the sequential loop, which is saying I is equal to 0, it does it for 1,000 steps. And we keep on changing I, where we take the value of A matrix and take the value of B and C matrix, multiply by it together, and store it in a new matrix. Right? That's the operation we are doing. But you can see that we are leaving these three registers unused. So in a calculation which uses 3 arrays, we are basically leaving 9 registers unused in each operation. So why don't we vectorize our code? By vectorization, we are saying instead of doing a single 32-bit operation, we are asking the processor to do 4 32-bit operation or a 128-bit operation in one go. It takes the same amount of time because we are not using all the registers, but instead we are basically accelerating the process. So now what we do is we basically write a vectorized code here where we can say A. Instead of incrementing it one thing at a time, I'm saying, let's do a chunk of 4. So you were previously doing it sequentially, right? You were taking one value from each index of the array. Now I'm saying, let's do it in chunks of 4. So it's like you had a car and you are going from your home to your university or your dorm to your university, and you're transporting every single person from the dorm to the university using your car. Your car is still can fit like 4 people at a minimum, but you're using only one problem. No, the diagram and the code is slightly off. It's addition versus multiplication, but it's exactly the same operation that's being carried out. Or the logic doesn't change in terms of figure. So in the vectorized code, what we are going to do is take 4 people at a time in a car. So we are going to take index 0, 1, 2, and 3 together, take the vector 0, 1, 2, 3 for B, add them together, and put it in the vector C. So what we've done is basically made the code almost 3 times faster because we are now using up all the registers. So the benefit is the performance will increase, but the code readability is pretty much remaining the same, but it looks slightly different from before. What you're seeing here is a C++ code that does multiplication of 2 matrices, whereas in Python, instead of trying to do this, we are going to leverage vectorized operations in Numpy. So we don't have to write a vectorized operation like this. Instead, Numpy already has a vectorized implementation which we could use. So every time you write a for loop, think, is it possible for me to not write it as a for loop, but instead as a vector operation? So for example, if we go ahead and look at the sign function in Numpy, so let me Google Numpy sign function. You can look at the manual here, and then it says this is the input. Numpy takes a variable x. It has some optional values, but if you look at the input is array length. It says the parameter x doesn't have to be a single value. It can be a list of values. So Numpy already has vectorized this operation, and so we don't have to do it one thing at a time. We can actually feed Numpy the entire array of time and multiply it by 2 times pi f, and that's it. Like give it a vectorized operation and be able to feed in the whole array, and Numpy will give us an array output because you can see the input is also an array and the output is also an array. So instead of writing a for loop like this, we are going to rewrite this, but instead use the vectorized version. Okay, so scroll down to the vectorized implementation, and here we are going to create a variable called signal1. And we are still going to use np.sign, but now we know that np.sign can accept an array. Remember, we have time t is already defined as an array in Python. This has size of n, where n was like 10 million. Right? So we're going to do this operation where it is 2 times pi, np.pi, times the frequency f, times the t. So previously we used the index notation to go each value in the array. Now we are feeding the whole array in one single go. So we have removed the for loop, which was a little bit more descriptive of what was happening, but made the code a lot simpler by writing numpy.2 times pi ft. Okay, so previously it took about 27 seconds on DesignSafe, so everyone should have similar execution time. Now you run it, it didn't even take any time. So as soon as you hit run, we can do it as shift and enter. That allows you to run the cell, or click on the play button here at the top to run the cell. You can see that it ran in 0.12 seconds. So same 10 million calculation ran in 0.12 seconds. But now, what if you want to go even larger? So here's like a cell with 100 million elements rather than 10 million elements. You can now initialize that 100 million elements and then compute the same thing. So if you do that here, it's still, oh, I didn't run this. So generate a 10 million cell and then run it. It should roughly take a second. So from 0.12 seconds times 10, because we went from 10 million to 100 million, we are roughly in that same operation range. Like if we had to write this in a for loop and do that compute, we would have taken almost 270 seconds, close to like close to 5 minutes. So that's why, like, look for vectorized operations. Vectorized operations are available plenty in Numpy space. So Numpy library can do vectorized operations and save you a whole lot of time. So that's one way to vectorize, is go ahead, use the Numpy libraries much more effectively. And the other option is use something called JAX. JAX is a Python library, which is basically Numpy, but significantly accelerated. JAX is mainly used in machine learning. It's a way to do automatic differentiation in machine learning. Machine learning is basically a bunch of linear algebra and matrix operations. So they have already accelerated your NumPy code significantly. One other benefit of using JAX is basically it can run on accelerators, by which I mean it can run on GPUs and TPU machines. So you can leverage JAX to run things on graphics card without actually changing your code. So I'll show at the end like how you can run your Python code written using NumPy, change one line, and you will be able to run it on both CPUs and GPUs. Of course, if you want to optimize, get the best speed up, then you need to incorporate those optimization schemes. But you can go ahead and do these very simple improvements to your code. So I previously said if you wanted to install something locally, which is not available, we can do pip install. JAX is there, but I'm going to use like the CPU version of JAX to go through this. Okay, so we're going to use JAX CPU. So you can go ahead and install JAX, and it's basically installing JAX and a few other libraries. So NumPy, SciPy, and what JAX does is basically accelerate our code, optimize it so it runs much faster than what NumPy will be able to do. So it says we have installed the CPU version of JAX, and it uses the JAX library. I'll also talk about how to run some of your codes on GPUs. So because DesignSafe runs on TAC, TAC has both CPU machines and GPU machines, and it's really, we can benefit from DesignSafe because we give you free access to those GPU nodes, and you can run like machine learning or other GPU-centric codes on DesignSafe. Okay, looks like we're all installed. So we're going to do the same operation like NumPy. If you look at the code before and now, the only thing I changed is instead of importing NumPy, I added jax.numpy and then imported as JNP. So the only thing I've changed is this line and calling JNP instead of NumPy. So execute that. That will generate a time series like before. And now just to demonstrate like it's exactly the same code, we're going to copy the signal1 variable, paste it down at the jax section, and we're going to use JNP. So previously, when I ran, I think this is the 100 million, right? It took about a second. So just to verify that it took about a second before. Now let's go ahead and change it to JNP, right? So we're just adding one extra character. And then clicking run, we went from 1.5 seconds to 0.35 seconds. So that's a significant speed up. So it's about 3 times faster than NumPy, and all you had to do was add an extra character. So one single character can make it 3 times faster. That's a very good benefit for running codes. And JAX is definitely faster at these operations, but it also has some odd code structure later on if you go outside of the traditional maps. So I did mention that there is a GPU node which you could use.
Krishna,
I am going to, yeah.
There's someone was having trouble, J1 was having trouble with the that error that you had. Yeah, with the dash.
So yeah, please add like -FN user, and it should be able to install it without problem.
And then some of the people who couldn't spin up the VM Jupyter were successful in spinning up a GPU HPC instance.
Okay.
So is there anything that they need to do differently to install JAX there?
Yeah, I'm gonna show that right now. So I'll show you. I think like if your DesignSafe is currently kind of suspended, I'll recommend reaching out to Tim Cockrell on Slack. Hope you're on Slack, and then he will be able to help you out with setting access to DesignSafe again. Scott can, I can type his name. You're looking for Tim Cockrell.
Yeah, he's the one who sent the email to.
Yes.
It says that the user guide has details on account creation or reactivation. So I'll post a link to that user guide here.
So I'm going to show you how to use the GPU version. So we haven't reserved the GPU node, so please don't try to do it live right now because there's quite a lot of you, about 67, 65 of you who might log in. So don't do it right now. It's a very quick demo. Won't take more than a minute to show, but I wanted to show how to run things on GPU. So first step, go to use DesignSafe, go to tools and applications. Okay, that will launch a window like this. You're going to go to the analysis tab here and click on Jupyter. Okay. So use DesignSafe, tools and applications, analysis tab, Jupyter, that takes you here. It then asks you to choose a version of Jupyter. So if you look here, there's the Jupyter version, which is what we are currently using. This version runs on a virtual machine, so you will get onto it instantaneously. So the next 2 versions, these versions of Jupyter are basically running on a compute node in our supercomputing cluster, which is the Frontera system at TAC. Some of those systems are CPU systems, and some of them are GPU system. So because you're logging onto a supercomputer, although you're using only one node in the supercomputer, it has much more memory and better processors. So if you have like more computationally intensive versions and you're willing to wait for a little bit of time to hop onto a serious compute node, then please choose Jupyter Lab HPC CPU or Jupyter Lab HPC GPU version. And since I promised I'll show you the GPU version, they both will look identical in terms of like what the commands are that we need to fill in. We'll choose Jupyter Lab GPU. Type how long you want to keep the Jupyter Lab instance going. So the shorter the time you choose here, the faster you will be getting up and running. So if you're doing a development work, choose like 1 hour and you'll almost instantaneously get onto the schedule. This gets automatically filled. It's something meaningful. So you can say like Jupyter, Python acceleration class demo. Like that helps me like what I'm trying to do. This is just name so I can understand what job it is. You don't have to choose anything. This basically writes all the outputs from this session to this particular location. It will tell you where it is based on the job name. And then once you have it, you can click run. I already have a version running, so I'm not going to do that. But once you hit run, you'll basically see a status window. So you can see here on the status window that I've launched a Jupyter version. It will say like updating, and then finally go from queued to running. Once it says it's running, it basically gives us a link to connect. So you're going to click on this link called Connect. That is going to take you to a new Jupyter instance. So you can see that our previous Jupyter instance was something like this, Jupyter.DesignSafe and your user ID. Now, if you look at my Frontera Jupyter version, which is running on the GPU, it will say frontera.pack.utexas.edu. That basically tells you if you're on a Frontera node. So I'm going to go ahead, and the benefit is all like Professor Brandenburg will go through our data depot in much more detail, but whatever data we have on DesignSafe is readily accessible to you through the Jupyter instances. It's available on the GPU instance. It's also available on the CPU and regular VM instance. So here I've basically connected to all the published data set. We have a data community data, training, accelerating Python, and I have this vectorized JAX exercise. Right? So the previous instance, how long did that take to run? 100 million, it took about 0.35 seconds on a CPU. So let's add one more 0 and maybe multiply by 5 just to make it larger. So we're generating our, hopefully I didn't make it too large. Oh yeah, I went too large. Greedy. Okay, 50 million or 500 million. Okay, 500 million got generated. So 5 times as big. So that took about 2.5 seconds to run, compared to Numpy, which will take significantly longer. So if you run this in Numpy, let's see how long Numpy takes. It takes a while to even create the time step. So this is going to take a while, just running 500 million steps. But our optimized JAX version took 2.5 seconds. So let's go ahead, do the same on our GPU version. So you can do this later just to see like how well it works. And in order to install a GPU version of JAX, what we are going to do is use this line. So we have pip install, updating the pip version. Then from CPU, which is what you had before, you're now going to use a GPU version of the code. So make sure you are on a GPU. Go ahead, install these 2 lines. This is when you do it. I know you're not doing it live with me. I've already installed it. And then if you run this, we are running on a GPU node. If you're not running on a GPU node, it will tell you that there is a problem. So once you have it, if you run the 10 million, that again takes the same amount of time. So let's go ahead, run the 500 million one. So let me just check if this the is this the same one I'm running here? I don't want to give you different numbers for different problems. Okay, same thing.
A lot of zeros.
Yeah, I should probably do how many zeros? 1, 2, 3, 4, 8. You can do 5e8. This might be a better representation, so you don't like end up counting badly. So, oh, this is a floating point operation, so I'm still stuck with 0. So 50,000. I had it here. Okay.
So a lot of people are having trouble getting JAX to load even after a successful pip install, which I don't understand why that's happening. But if that is happening, I think we're not going to use JAX after this, right, Krishna? It's just Numba and
yeah, we're not going to use this particular version of JAX. It might be a JAX lib issue, so I can.
This is mostly
so JAX has
VM version, not an
JAX has. This is the VM version that they have problem. VM should have JAX.
Yeah.
But if you have a problem, I would recommend is if you're running into JAX problem, just do pip install user JAX. So that will install any additional JAX library that is needed. This will make sure it installs a particular version for CPU, but JAX will help you run it. And if that doesn't work, there's also the additional JAX and JAX lib to get it running. So try this and let me know if that fixed it. If not, we'll look into that. So last step is getting the vectorized version on the GPU node. So what took about, we are already running on the GPU node. Now it takes only like 1 second, whereas CPU was taking about 2 and a bit. So 2.5 seconds. Now our GPU version takes only 1 second to do the same problem. Of course, like as your problem becomes more complex, you will see the benefit of running it on a GPU even more significant. But we do have GPU nodes. You can access it through the DesignSafe portal. So go to Tools and Applications, launch a Jupyter instance, but you can see that GPU versions are faster. Okay. So now let's go talk about a heat flow example. So if you did the scientific computing workshop, which Charlie Day ran like a few weeks ago, that was on scientific computing. So he solved the heat flow problem. So if you haven't, you can go watch it on YouTube. We're going to do a 2-dimensional heat flow problem. So we have a square domain of 50 units by 50 units. We are going to apply a heat source at the top and look at how heat is being transferred into the material through conduction. Okay, so it's a typical civil engineering problem of heat flow, but it's the same governing equations if you're doing like fluid flow type problems. So if you're modeling soil and looking at pressures, or you're modeling any type of flow problem, this is your equation. So our governing equation is PDE, where we are looking at the temperature gradient, dou T with respect to time. Is going to vary in space as a second order derivative. So we have a thermal diffusivity constant, which is the material property or how quickly the heat is going to be dissipated. And this is the equation we want to solve. Typically, if you have a PDE like this, we are going to discretize it in terms of time and space using a finite difference operation. This is a first order finite difference. So you're basically saying temperature at time step k plus 1. So here we're doing finite difference. So this is time step k is the current time step. K plus 1 is the next time step. So you're looking at what is the temperature gradient between time over a time increment delta t. You do the same, but now we have like the second derivative of time with respect to space and x and y. So you're looking at a given node. So remember, whenever you're doing like finite difference, you basically have a grid, right? And at the nodes is where you're going to measure the temperature. So let's say this is our node I comma j, right? This is I and j, and we are going to, when you're taking spatial derivative, you're going to look at t I plus 1, that is the node to the right. So this is going to be I plus 1 and on a given j, and this is the temperature at node I minus 1, right? So we are saying temperature at node I plus 1, temperature at node I minus 1. So add these two values, subtract what's in the middle twice, divided by delta x. Delta x is the spacing in your grid. So you do the same operation again in y, but instead of looking at the row values, you're now going to look at the column values, where this is going to be your j plus 1 index, and the bottom is going to be your j minus 1 index. So those are the finite difference in terms of space, and the first part is the finite difference derivative operation in time. So what we are going to do is go ahead, put that into our PDE. So like we rewrite the original PDE in terms of difference in time, that's di k plus 1 and k. K is going to be our time index, I and j are going to be our space index, and we multiply by the thermal diffusivity coefficient alpha. So what we now need to do is like what we previously did, time as a one-dimensional vector, if you're going to generate time as a one-dimensional vector, but we're also going to have the space in a 2D vector. To make our life easier, we're going to assume that the grid spacing in our finite difference is same both in the x and the y direction. So delta x is same as delta y. That simplifies our equation. So we have a common denominator, which is delta x squared, and then we can add all these together. So we are looking at all the 4 points, which are at I plus 1, I minus 1, j plus 1, j minus 1, the temperature at those nodes to inform what is the temperature at the next time k plus 1. Right, put it in the equation. We have it's an explicit scheme where we are marching in terms of time, and explicit schemes are all conditionally stable. And in order to be conditionally stable, we want to make sure that based on our thermal diffusivity coefficient, this term for alpha delta t or delta x squared should be less than 0. That gives us delta t, so we can solve for this to be delta t, which makes us a very simple equation in terms of gamma, where gamma is just a function of thermal diffusivity coefficient, delta t, and delta x squared. All right, so that's all we have. So this is the implementation that we need to do, is we are going to march forward in time. Time is going to be one of the vector, and then we have a two-dimensional matrix in terms of space. Okay, so I want you to go to the top. You can hit the exercise here and say open in DesignSafe. Right? That will launch a heat transfer flow problem. Hopefully now this link works for everyone. If you go ahead and refresh it, the old link should also work now. But scroll all the way down, and you can see here we have created an array to store the value of time. And we're just writing a function. We don't know what the dimensions are, which we'll come to later. We're just implementing this part of the code, which is a finite difference operation of heat transfer. Okay. So once you're ready, I can see that the first operation is in terms of time. So this is the time loop. Then we have two loops, which are in terms of space, going up to 1 to nx minus 1 and 1 to ny minus 1. Because the x and y dimensions are the same, we are using nx to represent both of them together. Okay, so the first step is to write down this equation, which is what is the temperature at time k plus 1 for the node I comma j. And the function is going to be gamma. Gamma is an input parameter, which is already pre-computed and given to us. And then you're going to write this operation, which is go through all the 4 neighboring nodes for a given node I, j. So we're going to start off with temperature at time k for node I plus 1, j, plus temperature at time k. Then you have I minus 1, j. Then you add, I'll make sure I stick to this, I, j plus 1. It doesn't matter if you're just adding 4 values of temperature, but I'm trying to make sure that we stick to these equations written back. Okay, so then you have k, I, j minus 1. Okay, that's all you need to do, and make sure you close the parentheses so gamma gets multiplied across these 4 temperature values. All right, and it returns an entire temperature array at the end of all the iterations. So we can actually go slice into it and look at what is the temperature of the entire field. So like based on this output, I will get a temperature which is 3-dimension. So I can do temperature at 0.0 like this, which will basically give me temperature at time step 0. All the way up to temperature at time step length of t, right? Which is, in this case, I don't know what t we're going to define, but like we can look at the length of t minus 1. This will give us the last time step value. So this allows us to look at what the temperature looks like, but we've done a finite difference implementation. So let's go ahead and initialize that. So once we've done that, so let's try to execute this, right? So I'm going to move this code a little bit here. So we can initialize and run this operation. And calculate how long it takes to do the Python operation. Okay, so we are going to initialize a dimension of size 50, do it for 1,000 time steps, and we're making sure our DT is consistent so that we are not going over the critical time step. And here we are initializing the temperature field, which is everywhere. It's going to be 0 except for the top where we are applying a temperature of 100 units. Okay, so let's go run this part of the code, and then we are going to calculate what is the temperature after all these simulations. So we can say t, this is the simple version of Python loops. We are going to call our function, which is calculate Python t, gamma. Right, and we already have defined a variable t here, which is size nt, which is the number of time steps, and this is nx by nx in terms of space. Initialize all the boundary conditions to the left, right, bottom, and top. Once you've done it, go ahead and run this loop. And if you want to time only one like operation, you can always do like percentage time, and that usually tells you how long that cell took to execute. So it took about 2.5, 2.6 seconds. So that's how long a typical loop with 50 by 50. So 2,500 grid points done for 1,000 time step took 2.5 seconds. Of course, this is a very, very coarse mesh. If you submit it for a homework assignment, that's probably okay. But if you want to do any sort of good analysis, that's too small. And so now, how do we speed up this operation so that we can leverage all the things we have learned so far? So the first step is for us to do a vectorized operation. So previously I said we have a lot of do it in terms of chunks. So I give an example of car taking one passenger versus car taking multiple passengers at the same time. But vectorized operations based on registers, so we can even take a truck or go for a bigger example like train, so fit as many people as you want, as you do like multiple registers, and also leverage threads as we do this parallelization. So we're going to initialize the same way. So we're going to initialize the number of time steps, which is going to be the length of our temperature array. The temperature array is a 3-dimensional array in space and time. So imagine like slices of 2D spaces represented in time. Then let's go ahead and initialize the nx, which is the number of grid points in our space. The size is exactly the same in x and y direction, so we only have nx defined. So where we did like the loops, we basically went from one index to another, and then we had time as a separate index. Here, we're going to do all of that in a single line. So we're going to say time is going to go from 1 to nt. Space is going to change from 1 to nx. And in the x direction, and 1 to ny in the y direction, but nx and ny are the same, so we'll keep it as nx. So what was our equation? Our original equation, let me try and copy this. So we have this equation for reference. So here, let me paste it. Right. So this is the equation we want to implement. Now we're writing it instead of a for loop. We are saying take all of these and do it as a vectorized operation. So you're not doing like one calculation in each loop. You're doing multiple calculation in chunks. So we're saying like for all the time steps, so which is going from 0 to nt minus 1. Remember, what we are storing is the next time step. So we are always going from 1 to nt, whereas in the actual computation, our temperature goes from 0 to nt minus 1. So for step 0, the next time step is step 1. For step nt minus 1, the next time step is nt. Right? So that gives us k plus 1. So 0 time step is k. K plus 1 is 1, which is 0 plus 1. Nt minus 1 is k. So plus 1 becomes nt here. So we are basically rewriting this equation in terms of k and k plus 1. And the index goes from nx minus 1. And then there's I plus 1 to I minus 1. So we are going to do 0 colon nx minus 1. So now add it to t. So here we have another temperature field. So now we are going to vary it from the temperature is always time is always the same, which goes from 0 to nt minus 1, but the space domain is going to change, which is 0 to nx minus 1, and here is 1 to nx. And then t, let's copy it so it's easier to do it 2 more times. Right. So here we have temperature. The next is change this here from 1 to nx, and here it's still 0 to nx minus 1. Then you have 1 to nx and 1 to nx. So we have all of them. This is ij value. So we have basically written this equation as temperature at time step k plus 1. This is going to be temperature at time step k. This is I comma j. I'm going to drop the k. Then this is I comma j plus 1. Then it is temperature I comma j minus 1. Sorry, this is I minus 1 j. This is I minus 1 j plus 1. I minus 1 j minus 1. What are we missing? Finally is I plus 1 and j plus 1. Right? So this is I plus 1. This is j plus 1.
Krishna,
Right.
I think we're missing gamma too.
Gamma, yeah.
I think we have an error. I'll fix that error.
Yeah. So we need to multiply by gamma. So we can, gamma is a scalar, so you're going to multiply over the entire vector operation. So yes, that's the equation we have implemented. But now we've done the whole thing in time and space, so we can run this function. It just compiles that function. It doesn't actually do anything. We're going to see, so the vectorized version is written. What happens if we do a just-in-time compilation, right? And then we'll compare the speedups. So just-in-time compilation is basically taking whatever we've done in Python, so whatever we used in terms of loops, and then make it so that it does just-in-time compilation. For that, you need two steps. One is import number. And the next is, this is the most difficult part of just-in-time compilation, but like what Professor Brandenburg said, it usually means you're writing one line about your function. This is a decorator operation in a Python, which basically wraps your Python code inside another function. So this is number.jit. And you basically say, yeah, I have written a Python code, but compile it and make sure there is no Python in it when you compile it. So you're not only saying like number.jit, so you can just say at number.jit, which will make it just-in-time compilation of this entire function. But if you want to make it even faster, you can say no Python equals true. What this argument does is basically make sure that I will write Python code, but the computer, and you basically ask the computer to remove any reference of Python and use like an optimized C or C++ code or Fortran code to an equivalent machine code to generate that output. So we can generate it. Now we have all these functions. So we're going to compare the time for a traditional Python loop, a vectorized version, and a number version. And what happens when you do just-in-time compilation is it is going to take your code, read it line by line, compile it into a machine code, and execute it. So there is an additional step of compilation. So when you do this operation once, it's going to compile it. And when it sees that same bits of code again, it will do it faster. So we could potentially run like this for a single time step and run for the rest of the time step to accelerate it. So you can see that when we run the same function for the first time, it's going to be slow. But when you run it again, it will be significantly faster. The difference in speed is because the first time it compiles and runs, and the second time it just recognizes which part of the code is being run and just runs that code really quickly. So let's go ahead, run all four of these. All right, and you can see that the Python loop took 2.5 seconds. The vectorized operation was us writing a operations like we were setting everything in a big train. So we're using all the threads, all the registers, and run it in a vectorized operation. But this is significant. That's not my vectorized operation. There's my vectorized operation. That is significantly faster. And it only took 0.025 seconds. So we are about like 100 times faster, right? Writing a vectorized version of the code. Whereas the first time we ran number, it took half a second, which is 4 or 5 times faster. But when you run it the second time, it's much faster than a vectorized operation. It's like I said 100, now we are like 1,000 times faster than our Python loop. So we took a Python code, added one extra line, and said no Python equals true, and that made it 1,000 times faster. It just means now whatever PhD would have taken you like 3 years, now you could have done it in 1 day. So that's the benefit of running. So okay, if you get an error, like if you've done pip install and it still doesn't recognize it, what I would recommend is go to kernel and then restart your kernel. So once you restart your kernel, it will pick up the packages you had just installed. Otherwise, the kernel doesn't know what package you just installed. So if you install number, like using pip install user number, go ahead and restart the kernel, and that will help you recognize it and run it. So try that and let me know if you still run into a problem. Okay. Someone says the second run. So Number is not vectorized. Number compiles it, so it might do auto vectorization. But we are not manually vectorizing a number code. It basically compiles and optimizes the Python code into a auto-vectorized, auto-unrolled loop operations and makes it faster. The second run is basically avoiding the time it takes to compile, and that's why it is faster. So if you want to make things faster, you could run the first iteration of the loop only once instead of running it like 1,000 times. And then you can run it for the rest of the time steps from there on. So I wanted to show one final thing, which is that the results are exactly the same. We didn't cheat, or we get incorrect results just because we parallelized it. But you can see here, like the code all give exactly the same results, despite it being 1,000 times faster. Okay. I hope like the restarting kernel worked for most of you. I don't know. Raul, not sure. We can.
Yeah, do you think it might be an issue with classic versus updated for the kernel or the image?
Possibly, yeah.
It may also
But
just be that everybody's on and it's having trouble or something, you know, who knows?
yeah, but typically, so it's not an error. That's just how Jupyter Notebook works, is when you install a library, you have to restart the kernel for it to be able to pick up that library is there. And once it is there in your user base and your account, you'll be able to use it as many times, which is why you didn't see me have to do that, because I probably did a pip install. But unless you log out, shut down everything, close all the things, then you would have to reinstall those libraries. In which case, make sure to restart the kernel, and that will help you run. Okay, I will give up my control. Sorry if I took longer. So Professor Vanderberg.
There is a question. Sibin John has
did I miss something?
hand raised.
Can you hear me?
Yeah.
Yeah.
We can hear you.
Yeah. One of my question is, what was the difference? Because if you are running, if we can run with any other kind of functions, which is predefined. So is that work with the number JIT application? Because someone is writing like a kind of interpolation. SciPy have an interpolation algorithm. So if I write a new function with that, we are calling with a subfunction from the SciPy interpolation. So is Numba will work well or not? Or we want to write independent functions?
It will definitely work if you're writing your own user-defined function. If you're writing something like uses SciPy or Numpy to do your operation, sometimes the JIT will work. Sometimes it won't, because it might not be able to convert certain containers like dictionary very well. So like, for example, I had to like import numpy.type list so that it can do certain operations here. So you have full control over your code, so you can like let Numba know what is the data type or data container, which is used at the backend on their Python version, and then it will be able to convert it appropriately. But if you use another library, then unless you have access to it, and if it requires you to add something to that, then you might run into a problem. Otherwise, it should be okay. So it's 50-50 if you're running another library or function.
Okay, thank you for your input.
All right.
But you can also take your NumPy, install it locally, and modify it. But I wouldn't recommend doing it unless it's essential.
Yeah, no, why I was asking to, so we have different scientific schemes already available in the market. So if we can choose that to in our functions, if we are writing in a loop instead of loop, we write as a function. So three-dimensional metrics, we can do that kind of interpolation. Right now, you are using 2D.
So it needs to compile what is being called, So
Yes.
it might not be able to do it since it might already be calling like a C code, for example.
Yeah. Yeah. Thank you.
In which case, JAX has like pretty good alternatives for everything in NumPy, and you could potentially use JAX. And
Okay.
I think it might be a similar issue for people who had JAX that they need to restart their kernel. We didn't do that. No, Numpa has nothing to do with NumPy because we look at this particular function, there is no NumPy. In this function, it is purely like a Python array. It doesn't have to be a NumPy specific things that needs parallelization. Usually, I meant like NumPy function, but like the arrays are NumPy arrays here.
Right.
NumPy arrays generally guarantees that the array is contiguous, and that helps a lot than just using like a Python array. But we are not using anything specific for NumPy function.
Oh, okay. One more
Yeah,
question.
you would not want to pass in a Python list, right?
Yeah.
It should be a NumPy array. Yeah.
Okay.
Yeah,
So
you could, but you could take like use a different type. Oh, Number has a different list of possible containers. So you just need to import the correct containers to handle those.
okay.
So Krishna, I want to show how to access the data. I'm not going to have time to go through my example.
Okay, I'm sorry.
Maybe we should
So
move
sorry,
on.
Scott.
Yeah, I just have another meeting in 5 minutes, so let me work through this one quickly. So I'm going to go through and just do the response spectrum example, but from the full code instead of the template, because we don't have time to go through it. But they're both available, and you can find these in community data. And the main thing that I wanted to show in this example was not necessarily how to do the faster coding. Krishna has done a great job showing that. There is some of that in this example too, to make it very quick and efficient to compute response spectra. What I want to focus on is how to access data that's in the published area. So I have to hide these. Zoom puts their meeting controls exactly where every other control is. So it's so hard to find things. So what this example does is it uses a published project that's in DesignSafe. This is one that I worked on a bit. So, if you go to the data depot, we do have this little published area. There's also a published needs area. So this is all of the data that was part of the Network for Earthquake Engineering Simulation, which was the precursor to NERI. So all those data are here too. This data set is just in the DesignSafe published area. So it's regular published. And it's project 3941. So you can do searches, find data sets and so forth that you're interested in. And once you have that data set that you want to work with, what you'll find is that you can actually see it over here. So if you're in the updated image and you're running Jupyter Lab instead of Jupyter Notebook, you'll see this little file browser on the side. And there is a NERI published folder. So if you click there, it has a list of all of these projects. The project name is not here. So you're probably going to have to go back and forth between the data depot and the Jupyter listing. So what did we say? This was 3941. So I happen to know that's pretty far down the list here, right? So here it is. Here we see 3941. And then there are a couple different flavors, right? So this project has multiple versions, and I'm going to use version 5. So if we go in here, you can start seeing this path form, right? We have NERI published, project 3941 V5. And so what we've done in this notebook is listed some paths to common locations where you might want to access data. So you can get into all of your projects, you can get into my data, you can get into the published data that were published by other people, and then you can get into needs. Now you can't change anything in a published project, right? You can only read-only access it, but you can read files from the project without having to download them and then upload them to your My Data space or something like that. So if we come down here to this cell, what I'm doing is showing this path right here, right? So the path to the published area is always home/Jupyter/NERI published. And then everything else refers to the project where you want to access the data. So I've got PRJ 3941 V5, and then I'm interested in getting acceleration time series data because that's what we're going to use to compute the response spectra. And I'm going to do it for the magnitude 7.81 Pazarchik event. So double click here. And now you can see the full path, which I've replicated through the rest of this line. We used very big folder names for this particular project with spaces and things like that. So that happens. Then what I've done here is used a function to return a list of all of the files that have an AT2 extension. So AT2 is a format for acceleration response or acceleration time series data. So if we just print those files and run this, you can see a list, right? There's all those files. So I'm going to clear the output and then we can move on. I also coded up this read AT2 folder or function for you because AT2 is a file format that kind of reads like a book. Every column has a fixed width and then there are numbers in it. And so you have to parse it to get the acceleration data in an array. And this function returns the acceleration array and the time step. So you get a scalar value here and then an array valued function or vector for the ACC. So I'm going to run this one, and then I'm just going to do the first 10 acceleration response spectra because running all of them would take a long time, right? So 10 is already done. I've read them and gotten a list of accelerations and delta time in here. One thing you can do too is I've had these lists. Now I'm parsing them as NumPy arrays instead. So if you want to do efficient calculations, it's very important to have them as NumPy arrays, like Krishna was saying, because those are all ordered and they're all of the same type and everything, which is good. Once you have those arrays, you can save them directly as a .npy file. So I found this to be very efficient. It's much faster to read the .npy data than it is to reparse all of the AT2 data. So if you do something that's heavy, like kind of heavy in terms of all of the work you have to do to get it into a NumPy array, you don't have to redo all that work over and over again. You can just store the data in this .npy file and then read it quickly, and it will save it and read it for you. So here, I'll save it. Oh, I think one problem is that I'm in the community data folder. So if you're running this in community data, you'll probably get this error. Community data is a read-only folder. So what you would have to do is copy this notebook to your own folder, but then all of the paths and everything will work just fine. So we can't, well, let's see. I don't think I have it saved in community data. Yeah, it's not going to load that .npy file anyway. But if you save this to your own folder, you'll find that it runs much faster to load the data as a .npy file. So then in the rest of it, I'm just doing some processing of the response spectra, right? Defining time and damping and then zero padding. And then there's a get response spectrum. And this function that uses a kind of a loop-based function here, this one is using two nested Python loops. So I can talk a little bit about it as it's running. It's looping over all of the spectral periods where we want to compute the response of the single degree of freedom oscillator. And then it's looping over all of the frequencies in the FFT of the acceleration record that we've computed. These records are pretty long duration. It's a big magnitude earthquake, so the length of the signal is pretty long. And you could see that it took 29 seconds for it to run. Then we do vectorized calculations down here. So this is the equivalent function. This is just like what Krishna was showing. There is one difference, right? This one has a new axis command. So this is a way to broadcast together two NumPy arrays that have different dimensions. So there's, I don't have time to talk much about it, but if you have questions about it, feel free to reach out to me. And then if we run it, this one is, should be much faster, right? 2.2 seconds instead, so like 10 times faster. And I think I'll just end there. There is this other JIT version as well, and it runs about 3 times faster on the second run. Well, let's see, that's about 5 times faster actually than the vectorized Python, which is similar to what Krishna was showing too, right? I think that's carrying 4 passengers instead of 1 or something like that. Anyway, we are out of time, so I'm going to go ahead and stop the share right there and thank everybody for coming. I just wanted to post real quick. Here's a link to the survey. I'll put it in the chat. So we do value your input. Oh, I'm trying to copy it. Somehow I'm not able to copy and paste that text. All right, well, we'll reach out to you with a link to the survey so that you can give us some feedback. We appreciate all your feedback on this. Thanks everybody for coming.
Yeah, thank you. Sorry, Scott.